Black holes are supposed to be simple. They are the universe's ultimate prisons. Anything that falls in can never get out. Not a rock, not a spaceship, not even a beam of light. That's why they're called black holes. They are the end of the line. For a long time, that was the entire story. A star collapses under its own weight. It gets so dense that its gravity becomes inescapable. It forms a boundary around itself called an event horizon. Cross that line and you're gone for good. The black hole just sits there, growing heavier with everything it swallows. It was a neat, tidy, and terrifying picture. But then Stephen Hawking came along, and he introduced a wrinkle. A huge one. He showed that black holes aren't entirely black. They glow very, very faintly. They leak energy back out into space. This glow is called Hawking radiation. This discovery wasn't just a small correction to our understanding of black holes. It broke physics. It created a paradox so deep that scientists are still arguing about it today. It forces us to ask a fundamental question about reality itself. Does the universe remember its past? Or can information truly be destroyed forever? To understand this, we have to start with the black hole itself, and then we have to dive into the strange world of quantum mechanics. So, what is a black hole, really? Imagine a star much bigger than our sun. For millions of years, it burns fuel in its core. This burning creates an outward push. It's a constant battle. The explosion in the core pushes out, while the star's immense gravity pulls everything in. As long as there's fuel to burn, the star is stable, but eventually the fuel runs out. The outward push stops, and gravity wins. In a catastrophic instant, the star collapses. All of its mass, trillions upon trillions of tons, rushes inward toward a single point. It crushes itself into a spot of infinite density. This point is called the singularity. The singularity is where our understanding of physics breaks down. It's a place where gravity is infinitely strong. But the important part for our story isn't the singularity itself, but the boundary it creates. The gravity around this point is so intense that it warps space and time. Close to the singularity, there is a line, a point of no return. This is the event horizon. It isn't a physical wall, it's more like the edge of a waterfall. If you're in a boat far upstream, you can paddle away. But once you cross the edge, you're going over. There is no swimming fast enough to escape. For a black hole, the current is gravity itself, and the thing you can't outrun is the pull toward the center. Not even light. The fastest thing in the universe can escape once it crosses the event horizon. This is the classical picture of a black hole born from Einstein's theory of general relativity. And in this picture, the event horizon is a one-way street. Things can go in, but nothing comes out. The black hole's mass can only ever increase. It can merge with another black hole and get bigger. It can swallow a star and get bigger, but it can never get smaller. It seemed like a law of nature. And it made a certain kind of sense. Black holes were the universe's final resting place. Then came quantum mechanics. Quantum mechanics is the set of rules that governs the universe on the very smallest scales. It describes the behavior of atoms and particles, and it is deeply weird. One of the weirdest ideas in quantum mechanics is that empty space isn't actually empty. It looks empty. It feels empty. But on a microscopic level, it's a boiling, bubbling sea of activity. It's a place of pure potential. This idea is called quantum foam. The universe has a sort of energy budget. At any given moment, it can lend out a tiny bit of energy, as long as that energy is paid back very, very quickly. This borrowed energy can pop into existence as a pair of particles. You get a particle and its opposite, an antiparticle. For example, an electron and a positron. They are called virtual particles. They exist for just a fraction of a second, and then they find each other, annihilate, and disappear. They pay back the energy they borrowed. This happens everywhere, all the time, throughout the entire universe. Empty space is full of these fleeting ghosts. Usually, this doesn't matter. The virtual particles appear and disappear so fast that they don't really interact with our large-scale world. They are just the background hum of reality. But Stephen Hawking wondered what would happen if this process occurred right at the edge of a black hole's event horizon. This was the brilliant thought that changed everything. Imagine a pair of virtual particles popping into existence right on that line, that point of no return. One particle appears just outside the event horizon. Its partner appears just inside. They are created as a pair, linked. But before they can annihilate each other and disappear, the black hole's gravity grabs one of them. The particle that appeared inside the event horizon is pulled in. It can never escape. Its fate is sealed. it will fall toward the singularity, but its partner, the one that appeared just outside the horizon, is now alone. It can't annihilate with its partner anymore. It's free. It flies off into space. To an observer far away, it looks like the black hole just spat out a particle. It looks like the black hole is glowing. This escaped particle is what we call Hawking radiation. But there's a problem here. A serious one. The universe's energy budget must be balanced. That pair of virtual particles was created by borrowing energy from the vacuum. When they annihilate, the debt is repaid. But now, one particle has fallen into the black hole and the other has escaped into the universe. The debt hasn't been repaid. The escaped particle is now a real particle carrying real energy away with it. Where did that energy come from? Hawking realized the energy had to come from the black hole itself. The particle that fell into the black hole is a strange beast. From the perspective of the universe outside, it can be thought of as having negative energy. When this negative energy particle falls into the black hole, it subtracts from the black hole's total mass. Think of it like a bank account. The black hole's mass is its balance. The escaping particle is a withdrawal. The particle that falls in is the debit that makes the withdrawal possible. The black hole pays for the radiation it emits. The consequence of this is stunning. Because the black hole is losing energy, it's also losing mass. Remember Einstein's famous equation, E equals 2? Energy and mass are two sides of the same coin. If a black hole is losing energy through Hawking radiation, it must be losing mass. This means black holes are not eternal, they shrink, they evaporate. This process is incredibly slow. For a black hole the mass of our sun, it would take longer than the current age of the universe to evaporate even a tiny fraction of its mass. A supermassive black hole at the center of a galaxy might take an unimaginable 10 to the power of 100 years to disappear. They are still swallowing more matter from the universe than they are losing to radiation. But the principle is what matters. They are not one-way streets, they do leak, and eventually, after an almost infinite amount of time, a black hole that is no longer feeding will evaporate completely. It will radiate away all its mass until there is nothing left. In a final flash of energy, it will disappear. This was a revolutionary idea. It connected the world of gravity general relativity with the world of particles quantum mechanics in a way no one had ever done before. Yes, it was a step toward a unified theory of everything, but in solving one problem, Hawking created a much bigger one. He created the black hole information paradox. So, what is information? In physics, information isn't just about names and dates. It's the complete description of a physical system. It's all the properties of a particle, its location, its velocity, its spin, its quantum state. It's the unique blueprint that distinguishes one thing from another. If you have two electrons, the information is what tells you that this is electron A and that is electron B. A fundamental rule, a cornerstone of quantum mechanics, is that information can never be destroyed. It can be scrambled, it can be hidden, but it can't be erased from the universe. Think about burning a book. You throw a copy of Moby Dick into a fire. The book is gone. The words, the pages, the cover, they've all turned to ash and smoke. It seems that the information has been destroyed. But according to quantum mechanics, it hasn't. In theory, if you could collect every single particle of smoke, every bit of ash, every photon of light and heat released by the fire, you could reverse the process. You could reconstruct the book. The information is still there, just in a very messy and practically unusable form. This principle is called unitarity. It's essential. It means the present always contains the full story of the past, and it will determine the full story of the future. The universe doesn't forget. Now, let's go back to the black hole. Imagine you take that copy of Moby Dick and throw it into a black hole. The book crosses the event horizon. All the information contained in its atoms, the specific arrangement of carbon and hydrogen and oxygen crime, falls into the black hole. The black hole gets a little bit heavier. So far, so good. The information isn't destroyed, it's just inside the black hole. We can't access it, but it still exists. But we know that the black hole evaporates. Over an incredibly long time, it radiates away its mass in the form of Hawking radiation. And here is the paradox. Hawking's original calculations show that this radiation is perfectly thermal. It's random. It's a featureless glow of particles. The temperature of the radiation depends only on the black hole's mass, not on what fell into it. A black hole made from a collapsed star would produce the exact same radiation as a black hole of the same mass made from a billion copies of Moby Dick. So what happens when the black hole completely evaporates? It's gone. The Moby Dick you threw in is also gone. All that's left is this random thermal radiation, but that radiation contains no information about the book. It doesn't know about chapters or characters or the ink on the page. The unique blueprint of the book seems to have been completely erased from the universe. This is a catastrophic violation of quantum mechanics. This is the information paradox. We have two fundamental pillars of modern physics in direct conflict. General relativity describes black holes as simple objects that swallow things. Quantum mechanics says information can never be lost. But when you put them together at the event horizon, they seem to break each other. Either information is lost when a black hole evaporates, meaning quantum mechanics is wrong, or something is wrong with our understanding of black holes and gravity. Physicists have been banging their heads against this problem for decades. It's not just a minor puzzle. It points to a deep flaw in our theories about how reality works. There have been many proposed solutions. For a long time, Hawking himself believed the simplest answer was the right one. He thought information was truly lost. He made a famous bet with other physicists, arguing that black holes destroyed it. This was a radical position. If information can be lost, it means the link between past and future is broken. We could never be sure of what happened before, because the evidence could have been erased. It would rewrite the most basic laws of science. Most physicists were deeply uncomfortable with this idea. It felt like giving up, so they looked for other ways out. One idea was that the information doesn't disappear. It's left behind. Perhaps the black hole doesn't evaporate completely. Maybe it shrinks down to a tiny microscopic remnant, a little nugget of Planck scale weirdness. This remnant would hold all the information from everything that ever fell into the black hole. The problem with this idea is that a tiny object would have to hold a potentially infinite amount of information. A huge black hole could swallow galaxies for billions of years, and all that information would have to be crammed into a particle smaller than an atom. It doesn't seem physically plausible. It also creates other problems with particle physics. Another idea, and the one that has gained the most traction, is that Hawking was wrong about the radiation being perfectly thermal. Maybe the information does get out. It escapes, encoded in the outgoing Hawking radiation. The radiation isn't perfectly random after all. There are subtle connections, tiny correlations between the outgoing particles. If you could collect all the radiation from an evaporating black hole and analyze it with a super powerful quantum computer, you could decode it. You could piece together the story of everything that fell in. The information isn't lost, it's just incredibly scrambled. It's like the burnt book analogy. The information is in the smoke, you just have to know how to read it. This is the aha moment for many. It saves quantum mechanics. Stephen Hawking eventually came around to this point of view. In 2004, he publicly conceded his bet. He announced that he had been wrong. He now believed that information was not lost. It was preserved, but in a way that was still not fully understood. But saying the information gets out is easy. Explaining how it gets out is much harder, and this is where physics gets really strange. It leads to ideas that sound like science fiction, like the holographic principle. The holographic principle is a mind-bending idea that comes from string theory. It suggests that all the information contained within a volume of space can be described by a theory that lives on the boundary of that space. Think of a hologram on a credit card. It's a two-dimensional surface, but it encodes a three-dimensional image. The holographic principle suggests the universe might be like that. The 3D reality we experience might be an illusion, a projection of information stored on a distant 2D surface at the edge of the universe. How does this apply to black holes? The idea is that when you throw your book into a black hole, the information it contains doesn't actually cross the event horizon and fall into the singularity. Instead, it gets smeared out and encoded on the surface of the event horizon itself. The event horizon acts like a giant, two-dimensional hard drive. As the black hole evaporates, this information on the surface is slowly imprinted onto the outgoing Hawking radiation. Each particle of radiation carries away a tiny, scrambled piece of the story of the book. By the time the black hole is gone, the entire story has been broadcast back out into the universe. This is an elegant solution. It preserves information, it connects gravity and quantum mechanics. It seems to solve the paradox, but, as is often the case in physics, solving one paradox created a new one. This new problem is called the firewall paradox. The firewall paradox is a sharp and nasty consequence of the idea that information gets out. It goes like this. Let's think about a particle of Hawking radiation that has just been created at the event horizon. Let's call it particle A for the information to be preserved. Particle A must be quantum entangled with all the radiation that has been emitted before it. Entanglement is a weird quantum connection where two particles are linked, no matter how far apart they are. Measuring a property of one instantly affects the other, so particle A is entangled with the radiation that has already left. This is how the information gets out, through these subtle entanglement connections. But remember how Hawking radiation is created. It starts as a pair of virtual particles. It's particle A, which escaped, and its partner, particle B, which fell into the black hole. According to the rules of quantum mechanics, A and B must also be entangled with each other. They were born as a pair. So now we have a problem. Particle A has to be entangled with the early radiation, and it has to be entangled with its partner particle B inside the black hole. There's a fundamental rule in quantum mechanics called the monogamy of entanglement. It says that a quantum particle can only be fully entangled with one other system at a time. It can't be married to two partners, so particle A cannot be fully entangled with both the early radiation and particle B. Something has to give. A group of physicists in 2012 proposed a startling solution. They said that the entanglement between A and B must be broken. As soon as particle A is created, its link to particle B must be violently severed. This break would release a huge amount of energy. The result would be a wall of high-energy particles right at the event horizon. At a firewall, anything trying to cross the event horizon would hit this wall of fire and be instantly incinerated. This creates a brand new paradox. According to Einstein's theory of general relativity, the event horizon should be an unremarkable place. If you were falling into a very large black hole, you wouldn't even notice when you crossed the event horizon. It would be smooth sailing. This is called the equivalence principle. It's a cornerstone of relativity. But the firewall theory says you wouldn't have a smooth ride at all. You'd be vaporized. So now we have another direct conflict. The holographic solution that saves quantum information seems to destroy Einstein's theory of gravity. So where does that leave us? We are at the absolute cutting edge of theoretical physics. The black hole information paradox is not a settled issue. It remains one of the biggest unsolved problems in science. It's a sign that our two best theories of the universe, general relativity and quantum mechanics, are not the final story. They work perfectly in their own domains, gravity for the very large, quantum for the very small. But when you try to combine them in the extreme environment of a black hole, the math breaks and contradictions appear. The struggle to resolve this paradox is the driving force behind the search for a theory of quantum gravity. This would be a single theory that can describe everything in the universe, from the flight of a galaxy to the dance of a subatomic particle. String theory is one attempt. Loop quantum gravity is another. These theories are incredibly complex and not yet proven. In the final years of his life, Stephen Hawking continued to work on the problem he had created. He proposed new ideas, suggesting that black holes might have a kind of soft hair, low-energy quantum fuzz on the event horizon that could store information. This might provide a way for information to be preserved without needing a destructive firewall. The debate continues. So, what is Hawking radiation? It is the faint glow of particles that black holes emit due to quantum effects at their event horizon. It causes them to lose mass, and over an almost infinite amount of time, to evaporate and disappear. Does it erase information? This is the billion-dollar question. The answer seems to be no. The consensus among most physicists today is that information is not lost. The universe does not forget. But the mechanism for how that information gets out is a deep mystery. The answer is likely tangled up in a new kind of physics that we have yet to discover. The story of Hawking radiation shows us how science works. It's not a set of facts in a textbook. It's a messy, passionate, and ongoing argument about the nature of reality. It started with a simple question about what happens at the edge of a black hole. It has led us to question the very fabric of space, time, and information, and it reminds us that the biggest objects in the universe, the black holes, are intimately connected to the smallest, the quantum particles. They are the ultimate laboratory for testing our most fundamental ideas, and they are telling us that we still have a lot to learn. The information isn't lost, it's just waiting for us to figure out how to read the message.